Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to try a little thought experiment with me. It's a bit of a terrifying one, but just bear with me for a second.
Okay, I'm with you.
Imagine you're standing out in a field. It's a clear night. The air is cold and crisp. Maybe it's winter. And you're looking up at the constellation Orion.
The hunter? Yeah.
You know the one. 3 stars for the belt, the sword hanging down, and that big, angry red star at his shoulder, Betelgeuse.
Can't miss it.
Exactly. It's a fixture. It's been in our story since we started writing things down. It's a cosmic landmark, an anchor for humanity, really. Now, I want you to keep your eyes on that red dot. Don't blink. Just watch it. And then, suddenly, the light just cuts out. No explosion, no beautiful expanding cloud of gas, none of that supernova stuff that turns night into day for a few weeks. It's there, and then it's not. A hole in the sky. A hole in, I don't know, in reality.
It gives you a physical reaction just thinking about it. It's unnerving.
It is, isn't it? It feels fundamentally wrong. Everything we know about physics tells us that energy doesn't just disappear. You know, massive objects don't just vanish into thin air.
Right.
If Betelgeuse winked out of existence tonight, the panic wouldn't just be among astronomers. It would be existential. It would feel like the universe just glitched, like a pixel in the simulation just went dead.
It would absolutely challenge our very deep-seated comfort with the permanence of the cosmos. I mean, we rely on the violent deaths of stars on supernovae to explain so much about us, where the elements came from. But silence is it's spooky.
And yet silence is exactly what we're here to talk about today, because this whole scenario, this impossible, terrifying, vanishing act, it's not hypothetical anymore. It actually happened.
It did, in a galaxy not so far away.
It didn't happen to Betelgeuse, thank goodness, for the sake of our night sky, but it happened to our next-door neighbor. We're looking at a report that was released just yesterday, February 12th, 2026. It was published in Science magazine with support from the Simons Foundation, and it details the life and the very, very sudden death of a star with, the distinctly unromantic name of M31 2014 DS1.
A name only a cataloger could love, for sure.
Exactly, but you shouldn't let that barcode of a name fool you. This star is at the very center of a mystery that's been nagging astrophysicists for decades. Really.
It has.
We are talking about the case of the failed supernova.
Which is a term that I think for most people just sounds like a complete oxymoron, a contradiction in terms.
It really does. When I hear supernova, my brain immediately goes to the most violent, explosive, ridiculously over-the-top event imaginable. So how does one fail? Did it just trip over its own shoelaces on the way to the explosion?
In a way, that's not a bad analogy. Kind of did. But the consequences of that trip they're just fascinating. What we're really discussing today is the clearest, most unambiguous observation humanity has ever made of a massive star collapsing directly into a black hole.
With no bang.
No bang, no fireworks, just a star that got too heavy, gave up the ghost, and crushed itself completely out of existence.
So this report is essentially the autopsy of a silent death. And what's really incredible to me is the detective work involved here. I mean, we're talking about spotting a single star blinking out in a galaxy that contains 1 trillion stars.
Yeah.
Located millions of light years away.
It's the ultimate needle in a haystack problem.
Yeah.
Except in this case, the needle suddenly decides to become invisible.
Right. So today, let's just walk through this whole investigation. We're going to look at the victim, this star, M31 2014 DS1. We're going to look at the murder weapon gravity. And then we have to look at the alibi, this new idea of stellar convection that explains why the star didn't just vanish instantly, but actually left behind this ghostly fingerprint.
And that fingerprint, that little bit of leftover glow, that's the key to the whole thing. It challenges a lot of our basic assumptions about how black holes are even born.
Okay, so before we get into the nitty-gritty physics of the collapse, let's just set the scene. We need to go to the Andromeda Galaxy.
M31, our big sister galaxy.
Right. It's about 2.5 million light years away. And I feel like we just gloss over that number way too often when we say this star vanished in 2016.
We mean the light stopped arriving here in 2016.
Exactly. The actual event, the death of the star, happened 2.5 million years ago.
Yeah, when Homo habilis was just sort of figuring out the whole stone tools thing on Earth, this star was already dying. We were watching a very, very old cosmic rerun.
That time delay always messes with my head. Okay, but let's talk about the star itself. M31 2014 DS1. This wasn't some minor player, was it? This was a big deal.
Oh no, this was an absolute heavyweight. The paper categorizes it as a massive star, but more specifically, we're looking at something in the neighborhood of 20 solar masses.
20 times the mass of our sun.
20 times. And in astrophysics, mass is destiny. There's no escaping it.
It's everything.
It is entirely destiny. A star like our sun, it'll die pretty gently. It'll puff off its outer layers. It'll become a white dwarf. It's a quiet retirement. But when you get above, say, 8, maybe 10 times the mass of the sun, you enter a totally different realm, the realm of violent deaths.
These are the rock stars of the galaxy.
They absolutely are. They live fast, they burn incredibly bright, and they die young and spectacular.
And usually they die loud. Very, very loud.
Usually. And M31 2014 DS1 was one of the most luminous stars in the entire Andromeda Galaxy. If you were an astronomer observing M31, this star was. It was basically shouting its presence at you. It was shining with the intensity of tens of thousands of our suns, a real beacon.
Okay, so it's a cosmic lighthouse, and it's 2014. The light from the star is hitting our telescopes. But it wasn't just any telescope watching it, was it? This is where the detective story gets really interesting. The main data came from a project called NEOWISE.
Right. And NEOWISE is a fascinating instrument in and of itself. It's a space telescope from NASA. Originally, its name was just WISE, the Wide Field Infrared Survey Explorer. And its whole job was to map the entire sky in infrared light.
So in heat radiation, basically.
Exactly. It's seeing what our eyes can't. It's seeing the thermal glow of the universe.
Yeah.
Now, WISE ran out of its primary coolant years ago, which normally is a death sentence for an infrared telescope, but NASA, very cleverly, repurposed it. They realized it could still be used to hunt for near-Earth objects, asteroids, comets, that sort of thing, hence the new name, NEOWISE.
So its main job is hunting for asteroids that might be on a collision course with Earth.
Primarily, yes. It sweeps the sky over and over and over again, and it's looking for things that move or things that change brightness against the static background of stars. But here's the beautiful unintended consequence. Because it scans the entire sky repeatedly, it inadvertently created this massive time-lapse movie of the universe.
Wow.
It wasn't specifically looking for a dying star in Andromeda. It just happened to be looking everywhere all the time.
That's the real beauty of big data, isn't it? You end up catching things you weren't even fishing for. So this team, led by a researcher named Kishal A.D., they're digging through all this archival NEOWISE data. What did they find? What's the timeline?
So they construct what's called a light curve, which is really just a graph of the star's brightness over time. And from about 2005 to 2013, the star is pretty stable. I mean, it's a massive bright object just doing its thing. But in 2014, its behavior starts to change.
It starts to get brighter.
It does. Specifically in the mid-infrared bands, the star starts to glow more intensely. It's a definite uptick. You can think of it like a fever. The star is becoming unstable. It's sick.
Is that unusual for a star this big? I thought they were kind of volatile anyway.
They are. That's a great point.
Yeah.
Massive stars are notoriously cranky. They burp, they flare, they pulsate. So a little brightening on its own wouldn't be a huge red flag. But this brightening, it continued, and it intensified until about 2016. And that is when the event happened.
The vanishing act.
The collapse. Between 2016 and about 2019, the light from this star didn't just fade. It plummeted. I mean, we're talking about a drop in luminosity that is just catastrophic. In visible light and in near-infrared light, it effectively went to zero. It was gone.
Okay, I want to clarify the terms here because the report makes a big deal about distinguishing between near-infrared and mid-infrared. Why does that distinction matter so much?
It's absolutely crucial to understanding the mystery. So near-infrared is a wavelength that's very close to the visible red light our eyes can see. It's the kind of light that a very hot object like the surface of a star emits. Mid-infrared, on the other hand, is a much longer wavelength. It represents cooler temperatures. Think warm dust, essentially.
Got it. So near-infrared equals hot star. Mid-infrared equals warm dust.
That's the perfect mental shorthand. So in 2016, the hot star signal, that's the visible light in the near-infrared, it just switches off. Poof. It drops by a factor of 10,000.
10,000. That's not dimming. That's...
It's gone. It went from being a stadium floodlight to a single candle flame in the middle of a hurricane. By 2022, 2023, for all intents and purposes, the star was no more.
If I were an astronomer looking at that data for the first time, my first thought wouldn't be, oh, a black hole formed. My first thought would be, did my telescope break?
Or did a satellite fly in front of the lens?
Right. Or did a big cloud of space dust just drift in front of it?
And the team had to rule out every single one of those possibilities. They checked for instrumental errors. They checked for what they call dust obscuration events, where maybe the star just had a massive boop and threw out a cloud of soot that temporarily hid it from view.
But those would look different.
They look very different. Dust clouds tend to dim the star in a particular way. They redden the light. They don't typically make the star disappear completely and so quickly. This was different. This looked terminal.
So to recap the timeline, we have a star that gets a fever. It brightens up in 2014. Then in 2016, it pulls the plug. By 2023, there's almost nothing left of it, except this faint, ghostly glow in the mid-infrared, the warm dust signal.
Which tells us that something is still there.
Yeah.
But whatever it is, it's not a star anymore.
Okay, so we have the body, or, well, the lack of a body, the crime scene. But to really understand why this is such a big deal, why this got published in a major journal like Science, we have to talk about how a star of 20 solar masses is supposed to die. Because going out quietly is not usually on the menu.
No, not at all. If you pick up any standard astrophysics textbook, you flip to the chapter on 20 solar mass stars, and that chapter ends with one word in big, bold letters. Supernova.
Let's break down that mechanism, because I think most people have the general idea of star runs out of fuel, goes boom. But the actual mechanics of why it goes boom, that's the part that failed here, right?
That's exactly where it failed. So a star is this beautiful, delicate balancing act. We call it hydrostatic equilibrium. On one side, you have the relentless, crushing force of gravity. It's pulling every single particle inward. It wants to crush the star into an infinitesimally small point.
And on the other side?
On the other side, you have the fusion engine in the core, the nuclear fire. It's generating a tremendous amount of outward pressure, radiation pressure that holds up the ceiling. It's constantly pushing everything out.
So it's like a permanently inflated balloon, but the air inside is a continuous nuclear explosion.
Precisely. For millions of years, those two forces are in a perfect tug-of-war. They're balanced. Now, massive stars are they're like onions. In the core, they burn hydrogen to helium. When that runs out, the core shrinks and heats up and starts burning helium into carbon. Then carbon into neon, neon into oxygen, oxygen into silicon. You get these layers upon layers of heavier and heavier elements.
Until you get to iron.
Until you hit the iron catastrophe. Iron is the end of the line. It's nuclear ash. You cannot fuse iron atoms together and get energy out of the process. In fact, it actually costs energy to fuse them. So the moment the core of the star turns to iron, the engine stops. The fusion furnace just turns off.
The outward pressure vanishes.
Instantly. The tug of war is over.
And gravity wins.
And it wins catastrophically. The core, which is about the size of the Earth but contains the mass of more than our sun, collapses into something the size of a city in a fraction of a second. This is the core collapse.
And this is where the neutrinos come in, right? Because I've read that the neutrinos are actually the real drivers of the explosion, not the collapse itself.
They absolutely are.
Yeah.
They're the secret ingredient. When that core crushes down from a white dwarf density to a neutron star density, it releases an almost unimaginable flood of neutrinos.
These are the little ghost particles that pass through everything?
Normally, yes. A neutrino from the sun can pass through light years of lead without interacting. But the density in this collapsing core is so beyond anything we can comprehend that even the neutrinos get trapped for just a moment. And in that moment, they dump a massive amount of their energy into the layers of gas that are still falling inward.
So the core collapses, it kind of bounces, it releases this wave of neutrinos, and that neutrino energy is what creates the shock wave that blows the rest of the star to smithereens.
That is the successful supernova mechanism. That's the script. The shock wave rips through the star's outer layers. It energizes them. We see a brilliant flash of light that can outshine its entire galaxy, and we get a beautiful expanding nebula left behind.
But M31 2014 DS1, it didn't do that. The shockwave apparently didn't make it out of the locker room.
This is the heart of the failed supernova scenario.
Yeah.
Imagine that shockwave starting to move outward. It's got all this energy, it's trying to push its way out, but it's pushing against 20 suns worth of heavy gas that is falling inward at thousands of kilometers per second.
It's like trying to stop a freight train with a leaf blower.
That is a perfect analogy. The shockwave stalls. The ram pressure, as we call it, of the infalling matter is just too immense. The shockwave creates a bit of a fizzle, maybe bubbles for a little bit, but ultimately it just gets overwhelmed. Gravity crushes it back down.
So the explosion is It's suffocated before it's even born.
Exactly. It's an engine that stalls on the launch pad. And all that material that was supposed to be ejected into space to form a nebula, it just keeps falling. It falls back onto the newly formed neutron star in the center.
And that's too much mass.
Way too much mass.
Yeah.
The neutron star crosses its stability limit. It's called the Tolman-Oppenheimer-Volkoff limit, if you want to get technical. And it can no longer support itself against its own gravity. It collapses further.
A black hole.
The event horizon forms. The star swallows itself whole.
Wow. That's a grim way to go. It's a cosmic suffocation.
It really is.
Yeah.
And for a very long time, this was just a theory. It was something we saw in computer simulations. The math would sometimes say, hey, for a star of this particular mass and this rotation rate, the shockwave shouldn't make it out. But we had never definitively seen it happen.
We see the black holes that are left over, and we see the supernovae, but capturing the moment of transition.
That's the holy grail of this field.
And M31 2014 DS1 is that holy grail. It's the missing link. It's the footage of the crime as it happened.
It connects the dots. It proves, observationally, that you do not need a spectacular visible explosion to create a stellar mass black hole.
But hold on a second. This brings us to the twist in the plot. And this is the part of the Simons Foundation report that really gets into the new physics.
Right, the problem of the lingering light.
Yes. If the star just collapsed directly into a black hole, if the shockwave failed, why did we see anything at all? Why did it brighten back in 2014? And more importantly, why is there still an infrared glow there right now? If it's a black hole, shouldn't it just be dark?
It's a fantastic question. It's one that stumped people for a while. If the collapse were perfectly spherical, if the star were just a perfectly still, non-rotating ball of gas, it would have just blinked out, gone in milliseconds. End of story. But stars aren't motionless.
They spin.
They spin and they churn. The report puts a huge emphasis on the role of convection.
Okay, so let's unpack convection in this context. I know convection from, boiling a pot of water on the stove. Hot stuff rises, cool stuff sinks. It creates a current.
It's the exact same principle, just on a nuclear galactic scale.
Mm-hmm.
The outer layers of a massive star like this, a red supergiant, are very loosely bound. They're boiling violently. You have these giant cells of hot plasma, some of them larger than our entire sun, that are rising to the surface, cooling, and then sinking back down.
That's incredible.
It's a chaotic, turbulent environment. But crucially, all of that churning motion preserves angular momentum.
This is high school physics coming back to haunt me. Angular momentum.
That's the ice skater analogy, right? That is the classic, perfect analogy. An ice skater is spinning with her arms stretched out. She pulls her arms in close to her body, and what happens?
She spins way faster.
She spins much, much faster.
Right.
That's the conservation of angular momentum. You can't just create or destroy that spin. It has to go somewhere.
Okay.
Now apply that exact same principle to the collapsing star. You have all this churning gas way out in the star's envelope. As gravity starts to pull it inward toward the newly formed black hole, it's like the skater pulling her arms in. That gas starts to spin incredibly fast.
It speeds up as it falls.
It speeds up so much that it eventually hits what we call a centrifugal barrier. It's just spinning too fast. The centrifugal force pushing outward starts to fight against the gravity pulling inward, so the gas can't fall straight into the black hole.
It gets backed up, like a traffic jam.
It forms an accretion disk. It goes into orbit. And this is where the report uses an analogy that I think is just brilliant. It comes from one of the researchers, Andrea Antoni at the Flatiron Institute.
The bathtub analogy.
The bathtub. Imagine a tub full of water. If the water is perfectly still and you pull the plug, what happens?
It just glugs straight down. It drains pretty quickly.
Right. That's a direct collapse without any rotation.
Yeah.
But if you get your hand in there and swirl the water first, give it some angular momentum, and then you pull the plug.
It creates a vortex, a whirlpool. It circles the drain.
And crucially, it takes a whole lot longer to empty the tub, doesn't it? The water has to lose that spin, that angular momentum, through friction before it can actually fall down the hole.
So the star, M31 2014 DS1, is a cosmic bathtub slowly draining into a black hole.
That's it. The water is the stellar plasma. The drain is the black hole's event horizon. And the swirling vortex is the hot, glowing accretion disk.
And the swirling explains the light, the glow that's left over.
It explains everything. First, friction. When you have gas swirling around that fast, rubbing against other layers of gas, it generates an immense amount of heat. We are talking about friction on a scale that releases X-rays and a ton of thermal energy.
So the drain itself is glowing.
The water circling the drain is glowing. But there's a second really important part to this mechanism. The energy from that friction, from that hot disk, it doesn't just sit there. It pushes back. It actually provides enough energy to drive some of the outermost material away from the star.
Wait, so the very act of feeding the black hole actually makes the star kind of vomit some of its material back out?
That's a violent but very accurate way of putting it. It ejects its outermost, most loosely bound envelope of gas. This gas expands out into space, away from the black hole. And as any gas expands, what does it do?
It cools down.
It cools down. And as it cools, it crosses a critical temperature threshold, a point where individual atoms of things like silicon and carbon can finally slow down enough to stick together. They form solid grains.
They form dust.
Cosmic dust. Soot, essentially.
Okay, let me see if I have the full picture here, because this is amazing. The core collapses, the big explosion fails, a black hole is born in the center. The outer layers of the star try to fall in, but they're spinning too fast, so they form a hot, glowing disk around the black hole, like water down a drain.
Yep, you've got it.
That hot disk then flings some of the very outermost material away from the whole system, and that ejected material flies outward, cools down, and condenses into a giant shell of dust.
A perfect summary.
And that dust shell, that's the curtain. That's what hides the star.
That's the curtain. Dust is incredibly effective at blocking visible and near-infrared light. It absorbs it and scatters it. That is why the star vanished in 2016. The dust shell basically hid the scene of the crime. And here's the absolute key to the infrared signal dust gets warmed up. It absorbs the intense heat coming from that inner engine, that hot accretion disk, and it re-radiates that heat.
It glows in the dark.
It glows in the mid-infrared. The dust shell is acting like a lampshade. You can't see the blindingly bright light bulb, the hot accretion disk directly anymore, but you can see the warm, gentle glow of the lampshade surrounding it.
Wow. That is such a satisfyingly complete explanation. It ticks every single box in the data. The brightening in 2014 was the star becoming unstable, the initial belch. The vanishing was the dust curtain forming. And the faint glow we see now is the warm lampshade, powered by the swirling drain underneath.
And it turns what was just a weird, confusing event into a clear physics lesson. It tells us that these massive stars don't just turn off. Even in failure, their deaths are incredibly dynamic, chaotic, and, well, messy processes.
So this brings us to the time scale of it all, which the report calls the long goodbye. You mentioned the bathtub analogy explains why it takes longer to drain. How much longer are we talking?
So if it were a simple freefall, a direct collapse with no rotation, the whole thing would be over in a matter of months, maybe a year at most. The star would be gone. Because of the angular momentum, the viscous time scale, as it's called, takes over. The material has to slowly lose its spin through friction, and that process, it'll take decades.
Decades. We're still watching it happen.
Oh, yeah. We will be watching this star slowly drain for the rest of our scientific careers. Andrea Antoni, the researcher I mentioned, actually calculated the accretion rates. It's a very slow feed. The black hole is just sipping at the material, not gulping it.
And how much of the star actually makes it down the drain in the end?
That's one of the most surprising parts of the simulation results. Their calculations suggest that only about 1% of the star's original outer envelope actually falls into the black hole during this initial bright phase.
Only 1%. That seems incredibly inefficient.
It turns out black holes can be very messy eaters. That angular momentum barrier is really, really effective at keeping material out. The vast majority of the star's outer layers are either ejected into the interstellar medium forever, or they'll hang out in a much larger, cooler disk for thousands of years. But that tiny 1%, that's more than enough to power the infrared glow that we're seeing today.
So M31 2014 DS1 is essentially a ghost. It's a black hole wearing the dusty corpse of its parent star, like a shroud or a disguise.
That is a very metal way to put it, but yes, fundamentally, that is what we are looking at.
I try, but this leads to the bigger question, right? You mentioned this is a Rosetta Stone. It helps us translate the data from this one event. Does this help us find others? Or is this star just a complete freak accident, a cosmic oddball?
And that's probably the most important takeaway from a scientific perspective. This is almost certainly not unique. In fact, as soon as the team understood the pattern they were looking at, the signature of brighten, then vanish, then leave behind an infrared glow, they did what any good detective would do.
They went back and looked at some old cold cases.
Exactly. They re-examined a different star, another one with a barcode name, NGC 6946BH1.
Rolls right off the tongue.
This one is in a different galaxy, the Fireworks Galaxy, which is about 22 million light years away. Back in 2009, this star did something very, very similar. It suddenly brightened up to about 1 million times the sun's luminosity, and then it just vanished from sight.
And what did they call it at the time?
At the time, astronomers just called it a red transient. They debated it endlessly. No one could agree. Was it a failed supernova? Was it two stars merging together? Was it some weird type of eruption we'd never seen before? The data was ambiguous.
But now
M31 2014 DS1 provides the template. It provides the key. They looked back at the old data for that star and the light curve, the timeline of events. It matches almost perfectly. It's the same signature. NGC 6946 BH1 was also a failed supernova. We just didn't have the high-resolution infrared data and the sophisticated models to confirm the mechanics back then.
So we're starting to build a family tree of these things. We're defining a new category.
We are defining a new class of stellar death. And this has huge implications for our census of black holes in the universe.
How so? What does it change?
Well, think about LIGO and Virgo, the gravitational wave detectors. For the past decade, they've been detecting the mergers of black holes. And a consistent puzzle has been that many of these black holes are surprisingly massive. We're seeing them at 30, 40, even 50 times the mass of the sun.
And that's been a problem, right? Because if a star explodes as a regular supernova, it blows a lot of its own mass away in the explosion. It shouldn't be able to leave behind such a heavy black hole.
Exactly. If you're a 60 solar mass star and you blow off half your mass in a spectacular explosion, you can't leave behind a 50 solar mass black hole. The math just doesn't work. But if you're a failed supernova,
you don't blow anything off. You keep all of that.
You keep almost all of it.
Yeah.
If the star just collapses and swallows its own envelope, the resulting black hole is much, much heavier. This mechanism, the silent death, might just be the missing production line for all of these unexpectedly massive black holes that LIGO has been seeing.
That connects the dots on a cosmological scale. The silence we're seeing here explains the gravity waves we're detecting from across the universe.
It really does. It suggests that failing to explode is actually a very successful way to build big black holes.
You know, this brings us to the more existential part of this whole conversation. And honestly, this is the part that kind of keeps me up at night.
The silent universe idea.
Yeah. We have built our entire understanding of the cosmos on the things we can see. The bright lights, the loud bangs. We literally count the number of supernovae we see to estimate how fast galaxies are forming stars. We use a certain type of supernova as standard candles to measure the expansion of the universe itself.
We are fundamentally biased toward the loud and the bright.
But what if we're missing half the picture?
That is the big, profound question that Kishley and his team are posing. If a significant fraction of massive stars, maybe it's 10%, maybe it's 30%, we don't know yet, if they die in silence, then our entire census of the universe is wrong.
It's like trying to count the population of a city by only counting the people who are screaming at the top of their lungs.
That is a perfect analogy. We have been completely ignoring the quiet ones. And this has other consequences, too. It changes the chemical evolution of a galaxy. Supernovae are the great dispersers. They forge heavy elements in their cores, the oxygen you're breathing, the calcium in your bones, and then they spread that material throughout the galaxy.
To be used in the next generation of stars and planets.
But if these stars don't explode, they lock all those precious heavy elements away inside a black hole's event horizon forever.
They hoard them. They take them out of circulation.
They completely remove them from the cosmic ecosystem. So the rate of failed supernovae directly determines how much stuff is available in a galaxy to make planets and eventually to make people.
So the story of M31 2014 DS1 isn't just a weird astronomical curiosity. It's a variable in the equation of life.
It really is.
And it makes you wonder, about things like the Fermi paradox. Where is everybody? Maybe the universe is just darker and quieter than we thought it was. Maybe advanced civilizations get swallowed in the dark along with their home stars, and we just never see the flash.
Oh, that's a dark turn. But let me offer a more hopeful counterpoint. Technology. The only reason we found this event is because we had the right kind of eyes. We had neo-eyes, which could see in the infrared. We have the James Webb Space Telescope now, which is even more powerful. We are, for the first time, developing the sensory organs to perceive the dark parts of the universe.
We're evolving our ability to see.
We're learning to see the shadows. And I think that's incredibly hopeful. We're finally realizing that the absence of light is also a form of information, a very powerful one.
The absence of light is information. I love that. It's very Sherlock Holmes. The curious incident of the dog in the nighttime.
What about it?
The dog did nothing in the nighttime. That was the curious incident.
Exactly. M31 2014 DS1 is the star that didn't bark. And because we finally noticed the silence, we learned something fundamental about how a black hole is born.
So as we kind of wrap this all up, I want to go back to that image of the bathtub, the swirling water, the drain. It's such a mundane, everyday image for something so catastrophic and so cosmic.
But that's the beauty of it. Physics is universal. The same principles of fluid dynamics and angular momentum that drain your tub after a bath also govern the death of a sun 2.5 million light years away.
That is either strangely comforting or deeply terrifying. I haven't quite decided which yet.
Why not both?
Both is good. So the big takeaways for everyone listening today, what should they remember from all this?
I think, first, massive stars don't always explode. Sometimes they give up the ghost and collapse. Second, this collapse isn't instant. It's a messy process. Convection and the star's own spin create this swirling, dusty death spiral that takes decades to unfold.
So it's a long goodbye.
It's a very long goodbye. Third, we can actually see this happen, but only if we look in the right kind of light in the infrared. The dust hides the visible star, but that same dust glows with heat. And finally, and maybe most importantly, the universe might be full of these stellar ghosts, and we are only just now learning how to look for them.
A universe full of ghosts. I'm definitely going to be thinking about that the next time I look up at Orion's shoulder.
Just keep a close eye on Betelgeuse for me.
I will. And if it blinks out, you are the first person I'm calling.
I'll be waiting for the call.
Thank you so much for walking us through this, and thank you all for listening to this investigation into the dark. It's just a reminder that sometimes the biggest discoveries happen not with a bang, but in the silence. So keep looking up, and don't be afraid of the dark.
Goodbye, everyone.